Hello, fellow pedestrians. In this lecture, like we said earlier, we are going to try and tackle the second order differential equations. But before we do that, let's talk about some other notion called linear dependence. Okay, let's assume that you are aware of a solution called y1 and you want to check if there's a second or a third or another solution of a differential equation. Doesn't matter which equation this is for the moment. Let's assume you have y2 and you write it as a function of x, y1. Now, if this function of x is indeed dependent on x, then y2 and y1 are linearly independent to one another. And if this is a constant, then they are linearly dependent. If u of x does not really have x. So if this is a constant, there are infinitely many solutions, which practically is the same solutions since they are all linearly dependent solutions. Now, if you go ahead and check the most general first order differential equation, which will be of the form y prime plus p of x y is equal to 0, and go ahead and plug this, assuming that this depends on x, and let's do that. You get u prime y1 plus u y prime plus p u of y is equal to 0. But since we know that y1 is a solution, and this is 0, meaning that this has to be 0, or u is just a constant independent of x. So you cannot have a second solution which is linearly independent, that is, to a first order differential equation. To put it in linear algebra terms and language, um, think of its differential equation, think of its order as the dimension of the space of solutions. So for a first order differential equation, you have a space of dimension 1, meaning that you only need one solution to construct your basis. Likewise, for a second order differential equation, let's write it down, q of x, y. For a second order differential equation, this has a dimension of 2, meaning that you need two linearly independent solutions to construct a basis, and to be more general than you can be. So of course each solution is going to be a solution. There's no asking about that. But to have the most general solution, you will need two solutions for a second order differential equation. For an order of n, you will need n solutions. And if you try and plug this in here, you will get a totally acceptable u of x that really depends on x. There is no u primes equal to 0. Now, if you try and plug a third solution, you will get something like that, meaning that you cannot have a third solution that is linearly independent. Every other solution except the two you find for a second order differential equation are going to be linearly dependent to the ones you already found. Right? And now, this is a second order t, and since we got this out of our way, let's try and tackle the simplest form of this, which is going to be y prime plus b y prime plus c y is equal to 0. Now, a, b, and c are reals, So they're just constants. That's why I said that we're going to try and tackle the simplest form of second order differential equation. Now, these three guys are real numbers, are just constants, and we need to be able to solve differential equations of this form. Now, an ansatz, which is an educated guess, could be of the form, you guessed it, e to the rx, because uh, this is a function that, regarding how many times you differentiate it, it's going to be the same and going to drop from every term. And you only get that the r term is going to be lowered down and you'll have to just solve a quadratic equation. So to see that in action, let's say you have this equation. This is going to be a r squared e to the rx plus b r e to the rx plus c to the rx. So equals to 0. These terms goes away and you end up with this kind of equation to solve, which is a very known quadratic equation with known solutions. Minus b plus minus b squared minus 4ac over 2a. Okay, and this is the solution every time. So you get one solution is going to be e to the r1x, and the other solution is going to be e to the rho 2x. So the final general solution is the linear contribution of these two solutions. So r1x plus the 2 e to the rho 2x. Right. This is a solution every time you solve this. This here is called the characteristic equation. And its roots are going to be next to x every time you solve differential equations of order 2 with constant coefficients. Now, there is an exception to this, and it is when you get a double root. If you get a double root, what happens? You can only have one solution. And what about the other? Then, like we said here, you're going to assume, well, not really assume, you know there is a second solution. It's just that if you have a double root, then it won't provide you with the information about this. So you go ahead and say that there is a second solution, which is written as ux times the first solution, which is going to be just e to the 1x, and you go ahead and plug this here. Now, if you do the calculation, you will see that this is just x. So what happens is when b squared minus 4ac is equal to 0, then we look for solutions. It's going to be y is equal to y1, which is e to the 1x and a constant, plus the second solution, which is this guy, and this is x. So 2x e to the rho 1 of x. In any other case, the solution is just going to be, like we said, e to the row 1 of x plus 2e row 2 x. Right? That's pretty much it. There's nothing more for for differential equations with constant coefficients. You just go ahead and solve the characteristic equation, and you find the roots of it. If it's a double root, then this is the second solution. If not, then you have these normal solutions. And so let's go ahead and check some examples. Okay, let's say we have y prime prime minus y is equal to 0. Go ahead and setting, like we said, the Rx. This will get you r squared minus 1 is equal to 0. So r is plus minus 1, meaning that y is equal to a constant e to the 1 times x plus another constant e to the minus times x. Okay, another example. Something I forgot to mention is that since you have two constants now in the second order differential equations, uh, you will need two initial conditions to be able to find to solve for these two, right? In the first order differential equation, we only needed one initial condition. Now we are going to need two, of course. So if you go ahead and for this example and check what happens if c of 0 is 0 and c prime of 0 is 1, you will get that this will transform to sine h of x. So the hyperbolic sine of x. Now, let's take another example. Y prime prime plus 4 times y prime plus 5 is equal to 0. So the characteristic equation r squared minus 4 rho plus 5 is equal to 0. And the roots are going to be 4. So it's 16 minus 20. So it's 2i over 2. And the solutions are 2 plus minus of I. Right. So the solution is going to be a constant e to the first root plus a constant the second root. It could be more neatly written 2x, another constant, ix plus minus ix. Right. And using de Moivre's formula, which is e to the I theta is equal to cos theta plus I sine theta, using this could be rewritten with different C1 and C2 as e to the 2x times C1 sine x plus C2 cos x. And go ahead and try it. It is indeed a solution to this differential equation. Now, let's take one more example. Y prime prime plus 2y prime plus y is equal to 0. The characteristic equation squared minus 2 rho plus 1 is equal to 0. But this has a double root. This is just rho minus 1 squared is equal to 2, meaning that you have a double root. And in this case, we go ahead and write the solution like we said it would be. The first solution into the solution, which is 1, so x, plus the second solution, which is x times this. And this is the full solution to this differential equation. Again, this and this are every time linearly independent. Here and here are linearly independent. Uh, of course, sine and cosine are linearly independent, and so on and so forth, right? We could do a lot of examples here, but this is pretty much it for the uh, second order differential equations with constant coefficients. Of course, we're talking about the homogeneous case. On our next video, we're going to check what happens when you have an extra term. So when you have y, let's say a constant y prime plus b y prime plus c y is equal function of x. This is a non-homogeneous differential equation, and we're going to check how to tackle it. Okay, so thank you all for watching, and I will see you soon on our next video, talking about constant how to solve second order differential equations that are non-homogeneous with constant coefficients. Thank you all.